You recall that we have we defined a micro-canonical ensemble. This describes a system that's isolated. It has an average energy E and particles N. It's isolated. That means it does not exchange heat, nor does it do any work on the environment. And then we next we define a canonical ensemble. And this is a system. We just take a small system out of this and ask what is its phase space probability. And then this is like taking this system and opening it up, let it in contact with a heat reservoir. And it exchanges energy. And the heat reservoir is characterized by a temperature T. So the energy of the system is no longer fixed, but it fluctuates about an average energy. But the temperature is fixed. So you have N particles at temperature T. And the volume occupied in phase space is called gamma E. That is the number of states of the system whose energy is E. And we said the entropy is K log this, and this establishes the connection with thermodynamics. Here in this case, the volume occupied in phase space is a partition function. And we say this is equal to E to the minus beta, Helmholtz energy, V and T. And this establishes the connection with thermodynamics. This, of course, is a more realistic description of physical systems because you never know the exact energy, but you can specify the temperature. So you just make this in contact with a large heat reservoir, and that fixes the average energy with a fixed temperature. So this is a more realistic ensemble, you would say, but they're equivalent because we show that the energy fluctuation is very small. And now we shall generalize this formula to the Grand Canonical. Now you must say that this is still not very realistic because you never know what N is. You take a glass of water. Do you know the exact number of atoms in a glass of water? You don't. You know the average number. It fluctuates about a certain number. So we also let N fluctuate. And you take the system. You keep the contact with the heat reservoir. So the temperature is T, and you exchange energy. But in addition, you exchange particles with another particle reservoir. And this is specified by a chemical potential mu. So so N is no longer fixed, but it fluctuates about an average value. And that average will be determined by the chemical potential mu. So this system is not determined by mu and T. Mu is chemical potential. So this would be the most flexible ensemble to describe a physical system. So we now ask, what is the connection? How do we get thermodynamics from this ensemble? So this is the partition function. So you ask, if I have a system in which N is not fixed, what then is the relative probability of finding N particles? At given temperature and volume. So the answer must be coefficient of Qn of V and T. This is what you have in phase space if you have n particles, times the probability of finding n particles, times z to the n, where z is sort of the probability of creating one particle. Is equal to this, and z is called the fugacity, and it's equal to e to the it's really the chemical potential is e to the beta mu, e to the mu over kt. Beta is of course 1 over kt. Mu is the chemical potential, and so this is the thing. And therefore, the volume occupied in phase space by this ensemble is the sum of this over all n, and that's called the grand partition function. Well, there's a script q. It's a function of z, v, and t, and it's defined as the sum of z to the n power, the partition function of n particles, v and t, sum n going from 0 to infinity. If we can deduce all the thermodynamics from this function, then we have find a connection between this ensemble and thermodynamics. First of all, the internal energy of the system U is nothing other than the average of the Hamiltonian over this system. So you can verify, I just give you the form. You can verify that this is equal to minus d by d beta of the log of Qn of t, log of z. Because if you do that to the Qn, you know that you find the internal energy of n particles. We went through that. So this is the internal energy. And therefore, we would expect that this per unit volume is a finite quantity. So we expect that U of V is finite when V approaches infinity. And therefore, log of Q, Z, V and T, this quantity divided by V, we expect that this approaches finite quantity as V goes to infinity. Therefore, Q itself goes like exponential to the V. So this is a good thing to bear in mind, that when in the thermodynamic limit, it's log Q divided by V that is expected to approach a limit. It's all included.
The meaning of n equal to 1.
N equal to 1, yes. The average number equal to 1. N is summed over here from 0 to infinity.
Yeah. When it's so small, you don't see the meaning.
It's the everything is done in a thermodynamic limit. For example, average N, average number of particles, N bar is equal to summation N, Z to the N, Qn, sum over N, divided by summation Z to the N, Qn. This is therefore equal to Z d by dz of log Q. So if you know log Q, you can get this. Now if I divide both sides, N bar over V, this is equal to Z d by dz of log Q over V. This is supposed to be finite, and this is expected to be a finite quantity in the thermodynamic limit. When n is 1 or 2, it's 0. In the thermodynamic limit, that's the density is 0. That's the density. That is, in a thermodynamic, we always make this go to infinity, v go to, and this fixed. So now, this is the average number of particles. Now we have to ask, what is fluctuation? Because the system that we talking about fluctuates about this average number. What is this? Is the fluctuation large or small? And this ensemble will not be very good if the fluctuation is large. So we better calculate the fluctuation. Of n. Now, we computed the fluctuation of energy in the canonical ensemble. And the technique here is similar. We know that you take the z, you get n, so we just do it twice. Consider z d dz done twice, z d dz on log q. This is equal to z d by dz. You know that this is nothing but summation n, z to the n, log q, divided by summation qn. So if you do this again, you just get summation n squared, z to the n, qn, summation log q. Sorry, yes. Let me I skip a step. Let me just write down one step. This is equal to z d dz. First, I have to differentiate this term and this term. First, I differentiate the numerator. I get summation n squared zn qn, and I leave the denominator untouched. And then I have to differentiate the numerator. So I get summation qn, this is z to the n, squared, and then I have to differentiate qn itself. So I get summation z to the n qn. That's from this, but there's one left over, so it's summation z to the n qn. So all in all, that you see that this is equal to, the first term is n squared average. I don't use a bar, right? This is a bar. The first term is just the average n squared. The second term is just the n average squared. So this is the fluctuation. So we have shown that the fluctuation is given by differentiating this log q twice by that recipe. Let us convert, since z is e to the minus beta mu, or mu over kt, d by dz, you can see it's just kt times d by d mu. So our formula is that if I divide both sides by capital V, you would say n squared over v squared minus n over v, this bar, and this bar squared. I just divide by v on both sides, just get the density. So I get n squared bar minus n bar squared divided by v squared is equal to kt squared over v times d by d mu squared log q over v. Now everything is finite. This is finite. It's n over v. This is finite, and this is 1 over v. So this would be very small if we can show that the rest is finite. So you would expect that this approaches 0 if this quantity remains finite. In order to do that, we now have to, so the fluctuation is small if this is finite. So to show that this is finite, we have to relate it to some observable thermodynamic quantities. So we should relate this. So we should relate this to an observable thermodynamic quantity. Then we can tell whether it's not as finite. And that will be an interesting exercise, and that's what I'm going to do next. In order to do that, let us compute the grand partition function in the following manner. Anticipating that the fluctuations will be small, we can make the following approximation. So anticipating that the fluctuations are small, that fluctuation in n are small, we can write log of q, which is equal to the log of summation n going to 0 to infinity z to the n qn. We would expect that one term dominates, the largest term. So this should be roughly equal to log of z to the n bar qn bar, where n bar maximizes the sum n. So this n bar is the largest term in that sum. And we can write this as n bar log z plus log q of n bar. Now this is just a chemical potential, so this term is okay. We want to express this in terms of observable thermodynamic quantities, and that's easy because we know the Q is how Q is related to the free energy. So now log Q n is equal to minus beta, the Helmholtz free energy for n particles, right? This is amount of V and T. This is A of V and T. This is the thermodynamic connection that we showed last time. For a physical system, the Helmholtz free energy is extensive. That is, it is proportional to the number of particles at a fixed density. So therefore we write A n of V at T is equal to proportional to n times free energy per particle times this. So A is this is the free energy per particle. And it's a function of the specific volume n t. V is equal to n over v. It's v over n. It's 1 over the density. So we assume that A has this form, which is what thermodynamics tells us. And now and the connection with thermodynamics is that I can get the pressure by differentiating the free energy, right? The pressure of the system is equal to minus dA n V of T dV at fixed temperature, at fixed V, at fixed N and T. And this is equal to minus d dV of N of A of V and T at fixed N and T, which is equal to minus N times d of A V and T dV, which is equal to minus d small v of A of V and T. So the pressure, if I know this, how most energy per particle, I can get the pressure right away by differentiating. Now the chemical potential is the pressure. The chemical potential is defined as this derivative dA n V and T, but this I'm taking this with n, dN, at fixed V and T. That is, it is the free energy per particle is the chemical potential. And this is, of course, just equal to d dV ddn of n of A. This V is V over n of T, keeping constant V and T. You can work out the algebra. The convenient end result is you get a formula that says mu is equal to A of V and T minus V times dA of V and T times dV. Now, using these two formulas, we can now express the thing that we want in terms of thermodynamic functions. That is, we can express this term in terms of thermodynamic functions. So you see, from these two equations, you can see that mu is just equal to A of B and T plus PB. Those two just imply this equation. And therefore, log Q, which is equal to N bar over KT times mu minus A of V and T. I'm just rewriting our previous formula in terms of mu and this. It is equal to PV over KT. So this is the important formula, Z, V and T. Once you do it by unit equation of state, PV equal to KT. This is a very nice result. And now if you want a second derivative, you just differentiate PV over KT. So this really shows that the Grand Canonical Ensemble is very convenient in computations, because in most computations, you want to know the equation of state of the system. You know PV equals KT. For the ideal gas, it's equal to 1. For the non-ideal gas, it's not equal to 1. What is it? It's the logarithm of the grand partition function. So if you do the Hamiltonian, in principle, you can compute this. Now let us compute the derivative of this to find out what the fluctuation is. And we'll find something very interesting. So n squared minus n bar squared, this is the fluctuation in density, is supposed to be equal to kT squared divided by v squared by d second derivative with respect to mu of log q. And this is, you can say this is equal to kT over v times dp d mu squared. So I have to compute this derivative. And if this is finite, then this vanishes because v goes to infinity. So let us compute it from mu is equal to a plus pv, which we derived before. The mu dv is equal to dA dv plus p plus v dp dv. But p is equal to minus dA dv. Cancels this term. And therefore the answer is just equal to v dp dv. And now dp d mu is equal to dp dv times dv d mu, because p is usually expressed as a function of v. And dv d mu we have computed over there. Therefore, this is equal to dp dv. Downside we would have d mu dv. And I plug this in, I get that this is equal to 1 over v. And therefore, this derivative which we want is equal to 1 over v dp dv. Just putting everything together. Now, this 1 over v dp dv, dv dp at constant temperature minus, this is defined as the isothermal compressibility. And it's measurable. So here we just have that thing in all of it. Therefore, our result is putting everything together. I have the final result. It says that n squared average minus n average squared, the fractional minus n average squared, is equal to kT over v times this isothermal compressibility. And that's measurable. It's usually finite. And therefore, this approaches 0. When v goes to infinity, if kT is finite. And therefore the fluctuation is very small. This is very small. It is microscopic unless KT diverges. Then you ask, does KT diverge? Interestingly, it does. It diverges at exactly one point at the critical point of a system. Everywhere is finite, but at the critical point, it diverges. And this is called critical fluctuation. Cap of t goes to infinity at critical point. But of course, it's not really infinity. It's cut off by atomicity, by the atomic nature. But theoretically, it's very large. And it just diverges suddenly at the critical point. What is a critical point? If you look at the PV diagram of a liquid, the isotope looks like this, right? In the phase transition. This is the gas phase. This is the liquid phase. And as you know, the gas phase and liquid, above the critical point, at the critical point, you cannot distinguish between gas and liquid. And above it, there's no distinction. And this one point is called the critical point. At that point, you see at this point, dP dV is equal to 0. And therefore, dV dP is infinite. So at that one point, the density fluctuation diverges. And that has dramatic consequences observationally. Because you know that this leads to the phenomenon called critical opalescence. Light is scattered by density fluctuations. That's a very important fact. If you have a system of scatterers, if you have fixed positions, then you send light in, you put a screen here to see what you get. You just get spots, diffraction spots, the von Laue spots. You get spots, diffraction spots. And the spots just tells you how these things are arranged in space. That's the principle of X-ray diffraction, right? That's how to find out how to find out the structure of a protein by X-ray diffraction. But looking at this, they found out, oh, it's a spiral. The DNA spiral, that's how they found it. But there's fixed spots, and there's no scattering. And if it's a regular crystal, you just get one spot, and that's index of refraction, that's diffraction. But if the position fluctuates, then in addition to the spots, you get scattering over all directions. So the scattering is due to the fluctuations. And if you look at this from the side, you don't see light unless there is fluctuation in the intensity. And this is why the sky is blue, right? Here's the sun. Here are the air molecules. The sun goes through the air molecule. If these are fixed positions, all it does, it just diffracts. Here, maybe it goes in some other direction. It does not get scattered. And if you happen to look at it this way, you see the sky is black. If you look at this, you go blind. So you either go blind or you go see black. No scattering. But because they fluctuate in density, you see a scattering background, and that's blue. Why? Because of Rayleigh scattering. It emphasizes the long wavelength. I mean, it emphasizes the short wavelength. And that's why when you look at the sunset, it's red because the blue has been scattered. So the blue of the sky is due to Rayleigh scattering plus fluctuations in the density of the air. And now let's come back to this. What if the fluctuation goes to infinity? The scattering is very strong. So if you take a liquid, let's take an example. In fact, for CO2, if you consider CO2, then the critical temperature Tc is it's 304 Kelvin. And the pressure at the critical point, is 74 atmosphere. That means if you just vary the pressure through this point, then light will not be scattered until you hit this point. Then suddenly it gets scattered. Theoretically, it's infinitely strong scattering, but practically, it's a factor of 1,000,000. It's not bad because it's cut off by atomicity. And then at this point, if this is CO2 here, light comes in here. Normally, you see normal scattering. At this point, suddenly this thing lights up. And it's called critical opalescence. The intensity increased by a factor of 1,000,000. So that's an interesting computation that you can do only in the Grand Canonical Ensemble, because you compute the density fluctuations. And by relating it to the thermodynamic quantities, you can see that normally it's very small until you hit that one point, the critical point. So we have now reviewed the micro-canonical ensemble, the canonical ensemble, and the grand canonical ensemble. To compute the grand partition function for the ideal gas is trivial because we know Qn already. So you just sum it up. So I'm not going to do that. And I think this will be a good break-off point for classical statistical mechanics and go to quantum statistical mechanics. So everything we're talking about is classical, but now let's talk. If you go to the quantum region, what modification do you need to make to our theory of ensemble and stuff like that? As a aside from our last discussion, you see that at the critical point, that critical point is a very interesting thing. The recent, more or less recent modern development in the theory of condensed matter, the theory of the critical point occupies a very important position. It was Wilson got the Nobel Prize for discussing the nature near the critical point using the renormalization group. And that's because at that point, the correlation length of the system goes to infinity. So that at that point, the system you cannot distinguish many properties of the system except for gross properties because the scale is so long. And that is a very interesting region of study, and I just mentioned this on passing. That's the method, called the physics of critical phenomena. Now we would like to discuss quantum statistics mechanics. when do you have to go to the quantum case? It's governed by the thermal wavelength. Lambda, which we have discussed it before when we discussed the kinetic theory. It's the square root of 2 pi h bar squared over mkt. It is the de Broglie wavelength of a particle whose energy is kT, or proportionate to it. And a dimensionless combination this is a length. So if I multiply this by n lambda cube, density is 1 over length cube. I have this quantity, which is a good thing to use to measure whether or not quantum phenomena are important. If this quantity is much less than 1, then you're in the classical domain. If this one is greater or less than 1, then you're in the quantum domain. Because this quantity is essentially lambda divided by the interparticle distance q. So if two particles, here's a particle, they're divided by distance r0, and lambda is sort of its diameter. If these are the same, then they overlap. The wave functions overlap, and you must use quantum mechanics. And so that's a useful parameter. And if you look at the say the Tn plane, the temperature is over n, and this n lambda cube equal to 1 gives you a curve like this. And this divides roughly into a quantum region and the classical. It will be classical here. And it's quantum here. And therefore, there's a temperature for given n. For given n, there's a temperature T0, at which the system will become quantum if you cool the system down below the temperature. And you can compute a temperature from this, and let us take a look at some numbers. K T0 is in fact just equal to 2 pi h bar squared over m times n to the 2/3. For given n, this is the critical temperature below which you have to use quantum mechanics. And see, for hydrogen gas, we'll make a table here. So look at various systems and see when do you have to use quantum mechanics. I just plug in some numbers for the mass of the system of the atoms and the density that usually is observed at room temperature. So I have, say, hydrogen gas, N, which is centimeter minus cube. It is 2 times 10 to the 19th. And you, in Kelvin, this one must be 5 times 10 to the minus 2. So for hydrogen, you have to go to very low temperature before you can feel the quantum effect. For helium-4 gas, the density is not much different. It's 2 times 10 to the 22. Number is different, but the mass is different. So you get 2 degrees. And indeed, at 2.18 degree Kelvin, helium becomes superfluid. At that point, you see the quantum effect. It's very dramatically manifested. You can see the superfluidity of the helium. So you see, you go from the 2. And what about electrons in metal? Consider them as a gas. The density is 10 to the 22, but the mass is so much smaller. So when you plug it in, you find that this is 10 to the 4th. What does that mean? That means that even at room temperature, the electron is very quantum mechanical. That is why the theory of metal, in the theory of metal, you have to use quantum mechanics. That's why all the classical theories fail. So they vary a lot, so it depends on the system. So now what do we do when we use quantum mechanics? I will start from here next after the break.